Hi, everybody. So today we're going to go over some example problems from the chain rule. So this will be chain rule part two. First part, we're going to talk about flow rate. So we're applying the chain rule to more real life situations. So a spigot is turned on and water is moving at a speed of V, begins to fill a straight garden hose of radius R and length L. At what rate is the volume of air in the hose decreasing? So first, let's write the rate that the volume of air is decreasing in terms of R, L, and T. So volume, okay, of a cylinder can be given as 2 pi R times the length of the cylinder. So we're going to call the hose a cylinder. Now, the rate that the volume of air is decreasing. So we're looking at the rate of change for volume. So when we want to write rate of change, we can also say that is the derivative with respect to time. Like when we say rate of change of position is velocity, we could say dx dt is velocity. Or the rate of change of acceleration is jerk, things like that. So the rate of change of volume can also be shown as dv dt. Okay, so that is what we're looking for. Now let's write velocity in terms of r, l, and t. So what is volume describing, or sorry, what is velocity describing the change of? Well, in this equation, 2 pi, they're just numbers. So we have radius and length that we could look at as variables, right? So, and I'm going to have to be careful on my v's, but we have little v, dv, dt. That's not the change in time, and it's not the change in radius, but is the change in length, right? So as the water moves down the hose, or as the air leaves the hose, that is a change in length over time. So we could say that that's not dv dt, that is velocity. So velocity is the change in length over time. Okay. Now we do need to remember that we are looking at the rate that air in the hose is decreasing. So in this case, velocity is going to be negative because we're looking at air in the hose decreasing, not water in the hose increasing, right? All right, so that was part one and part two. Now let's look at part three. Let's use geometry and the chain rule to solve this problem. So if we want to find the derivative of volume with respect to time, okay, what we can do is we can say that this is the derivative of volume with respect to the length times the derivative of the length with respect to time. And how I'm doing that is I'm using the Leibniz form of the chain rule, where if you want to take the derivative of some function z, you can, with respect to time, you can take the derivative of z with respect to y and multiply that by the derivative of y with respect to time. So you can break apart your derivative into different forms. Because if we just took the derivative of that volume function with respect to time, we would run into a problem, because this is what we want, but there is no time in this equation here. So you wouldn't be able to take the derivative. But what we can take the derivative of is that equation with respect to length, and we do have the derivative of length. So this guy right here, derivative of length, we already have. That is velocity, right? Now what we need is the derivative of volume with respect to time. So what is the derivative? Oh, hang on. We want to take the derivative with respect to time of 2 pi RL. I'm sorry, I wrote that wrong. we want to take the derivative of volume with respect to length, because we need this right here. And that would be d over dl, and the L is there. So if we were taking the derivative with respect to x of x, that would be 1, right? If x is squared or cubed, then you use the power rule. But if it's just the derivative of a variable, that derivative is 1. So the derivative of volume with respect to length would be 2 pi r. 2 pi r. The L would go away because the L becomes a 1. Right, now we have dv dl, we have dl dt. So if we want the derivative of volume with respect to time, we have derivative of volume with respect to length times the derivative of length with respect to time. So derivative of volume with respect to length is 2 pi r. Okay. And then we multiply that by the derivative of length over time, which would be negative velocity, right? So this comes out to negative 2 pi v r. So that is how we can find the derivative of that flow rate. So the flow rate, we can see, is determined by two variables, the velocity of the water and the radius of the hose. If those two change, then the flow rate will also change. And now remember, the reason that it's negative is just because we're looking at the rate of the air decreasing in the hose, not the rate of the water increasing in the hose. Okay. All right, let's move on to the next one. A toy needs the chain rule. So we have two objects, A and B, are connected by a rigid rod that is length L, and the objects slide along perpendicular rails as shown in the figure below. So you can see as A would move closer to the rail, B would slide further up, and as B slides down the rail, A would slide further to the right. So if A starts sliding to the left with a constant speed of VA, we want to find the velocity of object B when the angle is 60 degrees. So this can get tricky. So let's break this down. What are we given and what are we asked to do? So our goal, right? Our goal is to find the velocity of B. Now, B runs solely on the x-axis, A runs solely on the y-axis. So we could say that the velocity of B is the change in y over time, just like the velocity in A could be said to be the change in x over time, or you could say the derivative of x or the derivative of y. Okay. Now, if we want to find the derivative of y with respect to time, let's look at our givens. We are given a constant speed VA. So we have VA. VA is dx dt. Now what we could do is break down dy dt. Let's say that's dy dx times dx dt. We have this given right here that we can use to our advantage. So let's look at the geometry. Okay, we've got our goal, we've got our givens. Let's look at the geometry of this. So this is a right triangle, and we can use Pythagorean theorem to say that x squared plus y squared would equal L squared. Okay, if we look at the perpendicular rails there. All right, so to take the derivative of y with respect to x, because we already have derivative of x with respect to t, that's just the velocity of A, which we are given. What we need is we need y in terms of x. So let's solve the Pythagorean theorem for y. So if we subtract the x over, we have y squared equals L squared minus x squared. And if we want rid of that square, Let's put this all under a square root. Okay. Now we have y in terms of x. We actually have something to take the derivative of. Now it's kind of tricky to take the derivative of a square root because there's no exponent there. So let's rewrite this as L squared minus x squared to the 1/2 power. Okay. Now, if we want to take the derivative of that, this looks familiar, right? We have a function taken to an exponent, so there are actually two pieces to this. So we can use the chain rule here. So let's take the derivative of the outside and then multiply that by the derivative of the inside. Let's take the derivative of y with respect to x. So let's take the derivative of the outside, then multiply that by the derivative of the inside. So let's bring 1/2 down times L squared minus x squared. Then subtract 1 from 1/2, you get negative 1/2. And then let's multiply that by the derivative of the inside. So L in this case is not a variable, it is a constant. Because we're taking the derivative with respect to x, not with respect to L. So L is just a number. So derivative of a constant is 0, so that goes away. So the derivative of negative x squared is negative 2x. Now we can simplify that. If we simplify that, the 1/2 and the 2 go away. So we have negative L squared minus x squared to the negative 1/2 times x. I should put that in a better order. Yeah, so negative x times L squared minus x squared to the negative 1/2. Now that's really long and messy, especially for having to now multiply that by v and call that good. However, if we look up here, y looks like it might be able to be substituted. This section here can also be said to be negative x times y to the negative first power. If we take this y up top, put that to the negative first power, we get this section here. So this could also be said, if y is to the negative first power, that's actually 1 over y, right? So we could say that is negative x over y. And that would be dy over dx. Now, that looks nice and pretty, but we can't have y in that derivative. We don't want that. There shouldn't be a y in there. So let's use a trig identity. If you look at our right triangle, okay, our normal right triangle, I know that's not a right angle. You have A and B, and if we are looking at the angle theta is down in this corner here. If we had A divided by B, that would equal tangent theta. Okay, that's just a trig identity. In this case, B is x, A is y. So here we have B over A, and we actually have negative B over A, so that could be said to be negative 1 over tangent theta. So let's rewrite this. Negative x over y could be said to be negative 1 over tangent theta, and that could be our dy dx. But 1 over tangent theta isn't very pretty, so we will say that is negative cotangent theta, and that is the derivative of y with respect to x. And that you can get very similar derivatives when you're taking the derivative using the Pythagorean theorem. So there is dy dx, cotangent theta, which goes right here, cotangent theta. And we already have dx dt, which is the velocity of A. So let me box out part of this so I can write over here. If we want to find the velocity of B, which is dy over dt, we can say that dy over dt is dy over dx times dx over dt. Dy dx is negative cotangent theta, And then dx dt is the velocity of A. So you'd say that the velocity of B is the negative cotangent theta of VA. So since we actually have an angle there, you could also say that this would equal negative cotangent 60 VA. And you could evaluate that to a number if you'd like. But those are your ways to find that answer. Okay. All right. Let's go over this last problem real quick. All right, 2.9. Do we always need the chain rule? So in this problem, we've got a big cruise ship that lost its hydraulics and is trying to stop before it hits a Golden Gate Bridge pier, as you can see down there. The function describing its velocity is 3 meters per second cubed t squared minus 7 meters per second squared t plus 8 meters per second. Joe is running toward the front of the ship to save a scared puppy. His velocity is described by the function 1 meters per second cubed t squared plus 3 meters per second squared t plus 1 meters per second. What is Joe's velocity with respect to the pier? So this is a kind of like a relativity question. So let's break this down. What is the goal? So our goal, right, is the velocity of Joe relative to the pier. So how fast is Joe approaching the pier? Because he's running towards the front of the ship, but the ship is slowing down. So our givens, we have the velocity of the ship, which is negative 3 t squared minus 7t plus 8. And then the velocity of Joe is 1 t squared plus 3t plus 1. Now, do we need the chain rule on this? Well, we're not looking at how something is changing with respect to time. In our previous problems, we've looked at how is the circumference of a circle changing with respect to time? How is the radius changing with respect to time? Then on the hose problem, how is the length changing with respect to time? And how did the volume change with respect to time? Here, we're not looking at how is Joe's velocity changing with respect to time, or even how his position is changing with respect to time. We want to know his velocity with respect to the pier. So this does not seem to be a chain rule problem. So what do we actually need to do to solve this problem? So this is a little different. We know Joe's velocity as he's running towards the pier, but we also know that he's being fought by the ship who is actually going in the other direction. So what we can do, this is an interesting trick that we don't get to do often. What we're going to do is we're going to add these equations together. So if we take Joe's 1t squared plus 3t plus 1, and we're going to combine them. So you have minus 3t squared minus 7t plus 8. So if you just combine your like terms, you've got negative 2t squared minus 4t plus 9. That is how you can do that problem. The reason that that works is because we already have the equation of Joe's velocity. Joe is running at the pier with that function 1t squared plus 3t plus 1. But the ground, the literal surface he is running on is moving backwards at that negative 3t squared minus 7t plus 8. So if he was not on the boat, we would just use his function, right? That's how fast he's running relative to the pier. But the ground underneath him has its own function because he's running on the ship. So then we are going to combine the like terms of the t squareds, the t's, and the constants to get that new function in meters per second. All right, so that is chain rule part 2. Those are the example problems that we have. After this, you've just got the take-home test for chapters 1 and 2, and then we will take our unit test over combined chapters 1 and 2.